Clemmensen reduction is the reduction of carbonyl compounds like ketones or aldehydes to the corresponding hydrocarbons. In other words, it allows the deoxygenation of carbonyl compounds to convert to hydrocarbons. Or you can say that the carbonyl functional group is converted into a CH2 group in this reaction. In this video, we'll talk about the reaction conditions and the mechanism. So let's begin. So as I said earlier, Clemmensen reduction allows the deoxygenation of these carbonyl compounds to convert to the corresponding hydrocarbons. So you can see that in this conversion, this carbonyl functional group is converted into a methylene or a CH2 in the presence of zinc amalgam and aqueous HCl. Clemmensen reduction is not the only method by which you can convert carbonyls into methylenes. Of course, there is another reaction, that is Wolff-Kishner reduction, which we will discuss later on, but at the moment we will focus on Clemmensen reduction. So let's see how the mechanism works out. So you can see that we are using zinc amalgam as a catalyst here to reduce these carbonyl compounds to hydrocarbons, which means that the reaction happens at the surface of the zinc metal. A couple of different types of mechanisms have been proposed for this reaction: a carbenoid mechanism and a carbanionic mechanism. And in some pathways, alcohols have been proposed, but as a matter of fact, alcohols are not the intermediates that are formed during this reaction. Because if that was the case, then alcohols would also be reduced to hydrocarbons in the presence of zinc and HCl, but that is not the case. So the intermediacy of alcohol is ruled out in this case. So let's see how this reaction goes forward. We have this ketone here, and as I told you earlier that the reaction happens at the surface of zinc. So zinc actually provides an electron to this carbonyl functional group here, to this carbon, and in turn this oxygen attacks zinc here. And so what we get as a result is a single electron species here, and this oxygen is now attached to zinc, which now has an unpaired electron because it has provided one electron to this carbon here. Now, because we have more zinc present in the system, this diradical will react with another zinc, and it will allow the removal of this zinc oxide. And at this stage, so zinc oxide is removed, and what we get as a result is this intermediate, like this. This intermediate then reacts with the acid that is present, the HCl. So you can see that we have carbon bonded to zinc, and because this is a carbon metal bond, this carbon will act as a nucleophile and it will attack this proton here. It will abstract the proton, allowing this zinc to get a positive charge, which will take the chloride ion here, and as a result we will have this. So an H is attached here, and we have Z and Cl here. Again, we have a carbon metal bond in which again carbon will act as the nucleophile. So another HCl molecule will be attacked, or another proton will be taken up by this hydrogen with the removal of zinc chloride and the formation of this hydrocarbon or the methylene group here. So you just saw that carbonyl or a ketone has just been converted to a hydrocarbon, or a carbonyl functional group has been converted into a methylene or a CH2 in the presence of zinc amalgam under acidic conditions. As I said earlier, that we have another reaction, that is the Wolff-Kishner reduction reaction, which is also used for this purpose to reduce carbonyls to methylenes or hydrocarbons, but that occurs under basic conditions. So you so luckily we have two different reactions, one operating under acidic conditions and the other operating under basic conditions. So if we have a molecule that has base sensitive groups, then Clemmensen reduction will be the reaction of choice for converting any carbonyl into a methylene. But if we have acid sensitive groups in a molecule and we want to reduce the carbonyl to CH2, then of course Wolff-Kishner reduction will be the reaction or condition of choice for that particular reduction reaction. So this is it for now. Thank you so much. See you next time.